Hi, this is Mohammed Tariq, and this is the simulation part of my graduation project at the Arab Open University. My graduation project is LiREAP, a lightweight, robust encryption and authentication protocol for securing in-vehicle communications. Here we have a simulation of a CAN network. We have two ECUs, two electronic control units. Each ECU is represented by an Arduino board and an MCB CAN controller. And this breadboard right here represents the CAN bus. Um, the two ECUs are connected to the CAN bus. The powered up ECU will represent a normal legitimate ECU, and the other one will represent the MECU, which is the master ECU. On the screen, on the right side, is the code running on the legitimate ECU, and on the left side is the code running on the MECU. The MECU will be sending an encrypted message repeatedly, and the legitimate ECU will be listening to the CAN bus and receive those encrypted messages and successfully decrypting them. Okay, let's power up the MECU now. Let's restart first the legitimate ECU. As you can see in the serial monitor, this is it's reading from the CAN bus. Now the MECU will start sending, as you can see. Actually, the plain text message is this hexadecimal value, which is 8E8732, etc. But every time the ciphertext will be different because each message is encrypted with a different nonce, which which prevents replay attacks. So each time the same message produces a different ciphertext because the nonce is different. As you can see, nonce is printed here, which is synchronized between the two ECUs. The other ECU each time decrypts different ciphertext but produces the same plain text. Okay. Now, if we disconnect the ECU, which is listening to the CAN bus, if we disconnect it from the bus, the nonce will still be incrementing in the other side in the MECU. So we lost the synchronization between the ECUs in the counter. But if we reconnect back the ECU to the bus, a few messages will be dropped because the nonce is not synchronized. However, a counter recovery mechanism took place, as you can see. If we stop sending again, if we stop sending, as you can see, few messages dropped here. Then the ECU sent a counter recovery request. On the other side, the MECU received the counter recovery request and sent the required counter. The other ECU received the correct counter, and the resynchronization took place. Now let's simulate a CAN injection attack. If an attacker um, br- bring brings a malicious ECU, well, let's call it the hijacked ECU, and connects it to the CAN bus and trying to send CAN messages, but since the attacker doesn't have the session key, which is used as the encryption key, he cannot send authenticated messages. So let's try just to connect it to the CAN bus and open the code running on the hijacked ECU, which will be injecting CAN messages. This is the code, just sending plain text messages without encryption because it doesn't know the encryption key. Now let's restart the ECU which receives messages. Okay, and let's power up the attacker's ECU. Now the attacker's ECU is sending messages. Okay, let's connect back the listening ECU to see the dropping messages. As you can see, the other ECU, the legitimate ECU, is dropping messages, and it's trying to resynchronize the nonce because the counter resynchronization mechanism is running as well, but the attacker's ECU doesn't know this, and it's keeping sending messages to the CAN bus, and the legitimate ECU keeping dropping those messages. So we prevented the CAN injection attack. Now let's try the CRAM mechanism, which is challenge response two-factor authentication used to distribute session keys. So um, let's open the code of CRAM. Let's close the previous one. Okay. Okay. Now this mechanism um, is used to securely send the new generated session key from the MECU to the rest of the ECUs. Now we powered up the master ECU, and the code, what the code does is updating the session key and sending the new session key using the CRAM mechanism. Let's upload the code and let's open the serial monitor. Okay. Now the current session key was this one, and it was updated following the hash chain mechanism. Let's connect the legitimate ECU and upload the code that will request the new session key. It will take just a second, as you can see. Okay, let's restart. I think the serial monitor didn't work here. Okay, now it's working. Let's restart it. Yes, as you can see, the ECU sent a challenge request. The master ECU sent the challenge. The ECU received the challenge and solved the challenge and sent back the challenge response. The master ECU received the challenge response and checked for its correctness, and authentication succeeded and sent the new session key encrypted, and the other ECU decrypted the new session key. That's it. Thanks for watching.